Yeah, it's interesting looking through the light. I can see you better like this. There's lots of room down front. All right, I want to welcome everybody to this panel session. My name's Rich Wahls. I'm a member of the program committee and from NASA. I'm going to quickly turn this over to our moderator, Jeff Slotnik, who's a technical fellow at Boeing and, among many other jobs, the chairman of the IAA CFD 2030 Integration Committee. And Jeff will take it from here.
Okay. Oh, that's right. I don't need that. All right. Good morning, everybody, and thanks for being here. So I'll serve as the moderator today. So we have a distinguished panel of guests that maybe, well, hopefully were in attendance this morning with Rob's presentation on cert by analysis. This is an important area that clearly very important to us from the Boeing company as well as Airbus. So we'll be talking about a lot of the challenges that we talked about this morning, but for those that were not in attendance, I'll just kind of briefly kind of review a little bit of what we talked about. So as Rob mentioned this morning, there's the original panel in 2017 at an AIAA conference in the United States. Many of the panelists here were part of that panel as well. We did talk about cert by analysis. We started an effort at that conference where we kind of developed this community of interest in cert by analysis. We came up with a recommended practices document that Rob talked about a little bit more, and we'll talk a little bit more as we go forward on that. And that led to a study, a NASA commissioned study on the technical roadmap of where to get, how we get to cert by analysis in the notional timeframe of 2040. So those two documents are the things that really kind of came out of the effort up to this point. And so now there's a number of challenges that we talked about this morning as well that will hopefully get into more detail with the panelists. So with that, what I will do is introduce all the panelists at one time. They have prepared remarks, 8 to 10 minutes worth. We'll go through each of those. And then the remaining time we'll have for question and answer. So I encourage everybody in the audience to please ask questions as we go when we're ready for that part of the panel session today. So starting on your left, Uwe Kerlin is an executive expert for loads within the Airbus group and a leading technical expert on the expert council of the Airbus Flight Physics Center of Competence since 2015. Uwe joined Airbus in 1987 as a loads engineer. He has held several positions, including head of loads and aeroelastics domain in Germany. He represents Airbus as a designated certification specialist in the area of loads and dynamics. He was also involved in the American Airlines Flight 587 flight incident. He moved into Toulouse in 2009, and was the Airbus architect and integrator domain leader before returning to flight physics in 2013. He holds a degree in aeronautical engineering from the University of Brunswick in Germany. Mike Rogers. So I'll just, yeah, that's right. Okay. So, sorry. Mike Rogers is project manager for the Transformational Tools and Technologies Project at NASA's Aeronautics Mission Directorate. Tcube develops physics-based tools, methods, and cross-cutting technologies that enable fast, efficient design and analysis of advanced aviation systems. Mike has a PhD in mechanical engineering from Stanford in 1986 and has been working at NASA ever since. He's a recipient of the NASA Exceptional Science Achievement Medal and the NASA Outstanding Leadership Medal, and is an associate fellow of AIAA. Olivia Fischer, who's in the middle there, is a senior research engineer with the School of Aerospace Engineering at Georgia Tech, where she leads the Aerospace Systems Design Laboratory's Digital Engineering Division. In that role, she leads and manages multidisciplinary research teams in the areas of digital engineering, digital twins and ecosystems, model-based engineering, systems engineering, digital factories, production analytics, and machine learning. She is an associate fellow at AIAA. She's on the ICAS program committee. She's involved with the AIAA Digital Engineering Integration Committee, and she's the co-chair of the Digital Twin Subcommittee on that IC. She holds a master's degree in various fields and a PhD in aerospace engineering from Georgia Tech. Cord Rossow is the director of DLR Institute of Aerodynamics and Flow Technology and an active head of the DLR facility flight experiments in Munich and Braunschweig. He has been the head of the configurations branch at the Design Aerodynamics Institute, as well as the transport aircraft branch head at the Aerodynamics and Flow Technology Institute. Cord received his PhD in aerospace engineering, specializing in fluid mechanics and fluid mechanics from the University of Braunschweig in 1984. And then finally, Gregg, whom you've heard this morning. I'll just briefly repeat his bio. He's a chief aerodynamicist and Boeing's principal senior technical fellow in commercial airplanes, has 44 years of experience in aircraft development from concept to entry into service. He's responsible for strategic direction of the flight organization within BCA, leads CFD activities across the enterprise, leads in some internal activities, efforts in predictive flight characteristics, and chairs the wind tunnel capability steering team. He received his Bachelor's of Science degree in 1987 from the University of Illinois and a Master's from USC. And Rob is an Associate Fellow of AIAA. So with that, I will turn it over to Uwe.
Thanks, Jeff, for the introduction. And I would like to share with you some thoughts on the topic which is called certification by analysis. This is the agenda, so I will lead you a little bit through why we are discussing that. I try to make a picture which I call the pyramid of certification by analysis. Then I'm going a little bit into find the right balance, and you will see what that means, and conclude with the challenge of all of that. Why we do that? So first of all, we want to avoid late surprises, typically in flight test, which is at the end of the development of an aircraft. We want to optimize and make it more efficient, the certification progress. And of course, we can use already existing capabilities, which we need anyhow for the development of the aircraft and maybe even for digital twins later on. And of course, all that in order to accelerate our development time and the time to market. And maybe there's one other aspect which I had not on the list here, which is maybe also a safety aspect. We have some flight tests which can become critical, so in order, there might be an aspect of avoiding that. The pyramid of certification by analysis. On the top of the pyramid, you see flight test, which is often done in order to show compliance to the authorities, which we call MOC 6, means of compliance 6. There's a number for each of those things, and Rob explained it this morning quite well. And on the other side, lowering on the lower side and providing all the stuff before we do the flight test, there's on the one side the experiment. And I call it by intention experiment because we should not limit that only to the aero part of the whole story, but in the aero, of course, it's wind tunnel testing. And this testing, independent of what you're doing, needs, of course, a certain verification of what you are doing. And on the right side, you see, and I call it modeling and simulation. You might call it analysis, but for me, it's the modeling and the simulation, because it might include also some pilot in the loop simulation tests. It needs its own verification. Coming back to the left side, I include in the experiment, and this is shown a little bit by the color, by the shading. Normally it should be a blue color for the experiment, but I made it a little bit greenish which is the color of the flight test, because what you can do also is to think about scale flight test demonstrator. It's still an experiment. And you might also use results of similar aircrafts which you had certified before. So it's a mixture of all those things. The modeling and simulation, of course, and we do that all the time, there's nothing new. We use already to prepare the experiments and also to prepare the flight test, for sure. The important part is the arrow from the left to the right, which is the validation part of it. And we saw it this morning with the CRM and some other stuff. It's all around the validation of our tools, and I would even extend that to maybe a chain of tools to the end result. And then the question is, how do we convince ourselves that we are ready for an application to say we don't go for flight test, but we do it purely based on analysis or simulation, before we go then even in front of an authority and ask the regulator to accept that. And then there's one point where we might even say we can go for the analysis, but we need data from different sources. We know that CFD at the edge of the envelope, and we saw it this morning again, there are some gaps here and there where we might need still wind tunnel testing, for example, in order to complement all these simulation results. And therefore, I believe data fusion becomes an important part in the whole story, at least for the next years. And that, of course, needs a verification by itself. And then we have all around that big circle, and we have discussed it also this morning, and we are discussing since the last 5 years on that. All that needs to be accompanied by a proper uncertainty quantification and management system. What does it mean? It needs to be somehow useful at the end of the day and not a pure mathematical approach. If we keep that in mind for a while, then the question is, what is the right balance? I'm convinced we will not, in the next 5 years, replace each and every flight test. Maybe we will never achieve that. But what we can try to do is, at least, to minimize it and to extend the simulation. So we have 2 directions, to the top and to the left, to do that, always keeping in mind that we need at least something to validate the whole stuff with. And there might be cases where we can come to the conclusion at the end of the day, let's do the flight test, even if it is late and we carry a certain risk to have surprises relatively late, but it might be at the end cheaper or even safer at the end of the day to do the flight test instead to try to convince first ourselves and then the regulators to do the certification by analysis. And also this balance might differ for different use cases. For a wind-up turn, it's a different story than for the VMU test or for any other thing you can imagine, Buffett or something which comes anyhow quite late. So what are the challenges? And we saw it this morning. We discussed in the AIAA group in the recommended practice document. It needs a robust configuration process and data management for sure. It needs somehow an idea to bring all these different elements of the modeling and the testing together, so that we have really also in the testing a kind of pyramid and a pyramid for the validation. It needs what Rob called this morning MBE, model-based engineering, smart exchange of model and data at all different development levels and times. Might include even that we need to build up surrogates for the overall aircraft performance. Uncertainty management, I mentioned. And I mentioned already the system of verification and validation. And last but not least, to find the right balance between experiment and numerical simulations. Thanks for your attention. I hand over.
Morning. So I'm going to talk today about NASA's contributions to the SERP by analysis effort. Let's see if the charts come up here. There we go. Okay, I just wanted to mention the Tcube project. I manage that project, the Transformational Tools and Technologies project. As noted there, we are really a foundational cross-cutting project within NASA to develop cross-cutting tools, which includes most of the advanced CFD work. Sort of underpinning all the things that our mission projects are doing, providing them better tools to do what they do. We've also been the project to support these vision studies that you've already seen earlier today. Back in 2014, our CFD Vision 2030 was released. That is a roadmap out to 2030, prioritizing critical efforts in CFD and coordinating across the different things there, the modeling, the high-performance computing, all those aspects to get to the needed capabilities of 2030. You've heard about the AIAA Recommended Practices Report about things that should be done to properly do CBA. And then about the same time came out our NRA, NASA research announcement that was looking at a roadmap specifically for CBA with a little longer timeline out to 2040. Here's just a piece of that roadmap over the longer timeline. Rob showed the full thing this morning. This is that near-term piece. And if you look in here, we identify sort of things that might be done sooner rather than later, where our computational techniques are perhaps already adequate to start addressing some of those things, certify them by analysis, or at least increase the fraction of the certification process that's done by analysis. And then as you move out on the timeline, those get more and more difficult. Of course, again, you're coordinating across the various swim lanes, like in Vision 2030, ensuring that as you move to these more difficult, computationally challenging, scale-resolving or eddy-resolving simulations, that you are writing those algorithms appropriately for the new high-performance computing architectures to take full advantage of that. So again, we're starting out on this roadmap path, and one of the first tasks is this high-lift ecosystem that you heard about this morning, and I'll talk more about that today. I want to just emphasize, too, that this goal of increasing the amount of reliability in our CFD or in our wind tunnel modeling of flight test is certainly aligned with the sustainability. You know, the quicker we can get our new ideas certified and into the fleet, the quicker we can reduce CO2 production and the faster we can have that impact. The less flight test points we need to certify a plane, the quicker that flight certification process is. So these are important tools towards accelerating towards this new future. Okay, Rob showed this morning as well. You can see sort of a near-term vision of gathering the needed validation data for this high-lift problem, takeoff and landing configuration. In the midterm, this eye towards multidisciplinary, like aeroelastic or aeroservoelastic sort of challenges to do that. And then ultimately a 2040 type vision challenge, this low-speed wind-up turn, which has a lot of complexity, and it'll be a while before we really have confidence that we can do that fully without doing the flight test. Okay, so let's step back to the nearer term, what we're doing here in the near term. We're looking at this high lift configuration, and you saw this figure earlier this morning, and you can see the complexity. This is why on the left you can see the full flight envelope. The hatched region indicates sort of where we have high confidence in CFD, where RANS does a good job of predicting the flow fields. What we're looking at now is to try and extend that region so that ultimately we could really predict anywhere in that flight envelope confidently with CFD and wind tunnel analysis. So you can see that left trapezoidal piece at lower speeds, that's the high lift configuration. It looks small in the envelope, but actually a very large fraction of the flight test points occur there, so it's important. So it's a good thing to tackle this early high lift challenge. You can also see the VMU circle in there. That's the minimum unstick speed that Rob talked about this morning. And then finally the wind-up turn at the top of the right trapezoidal-like area. So a lot of new physics in there, a Buffett boundary. We're starting to look at Buffett as well, trying to understand, can we do better there with the tools? But the near term, the high lift configuration, you can see we have plenty of complexity. Flaps coming out, vortices off the edges, vortices off the chine, separation, not from sharp corners, so there is some of that too, but just off the wing, this smooth body separation where really viscosity and Reynolds number play a key role there. We have to get the right physics at the right Reynolds number. And in fact, that impacts the validation experiments that we're doing and what facilities we can use to try and achieve those high Reynolds numbers. For our particular project at Tcube, we have a headquarters endorsed technical challenge to develop and demonstrate computationally efficient eddy resolving or scale resolving, the same thing, modeling tools that predict maximum lift, CL max, for transport aircraft. And again, this verbiage with the same accuracy as certification flight tests. And Rob showed you that the certifications call for that comparable accuracy. So that's tough to define, but we need to achieve it. So what do we mean by these eddy resolving simulations? Well, RANs, the hope with RANs is that you can just look at the mean profiles of interesting statistics, and then the turbulence, the effect of all those complicated motions. You can just find maybe one equation to characterize the turbulence, or more commonly 2 equations, a time scale and maybe a velocity scale. And that there's sufficient information there to use those same turbulence models across any number of situations. Of course, that's a little overly simplistic. You can see this situation, the turbulence out there in the wing, where are there none of these vortices, that may look very different than the turbulence in those complicated structures. And what that really means is the turbulence is not generic enough to do with RANs. We need to actually start resolving some of those larger structures. We need to put in enough computational mesh to capture those and really just rely on the modeling to do smaller scale stuff. And that's so-called large eddy simulation. Large eddy simulation is one of the eddy resolving approaches. And so we've been working on those kind of approaches for a number of years. And as Rob mentioned this morning, we're starting to see some promise, some success in those. Here, for example, you can see a RANS prediction of, in this case, the Common Research Model on the left, the high lift variant, and then a wall-modeled LES simulation in the middle, and finally some data from the Kinetic test, in this case, of the same configuration. And this, you can see the point here, RANs, you have this large outboard separation that we don't see in the experiments, whereas the inboard is not captured, whereas wall-modeled LES, we match much better what we see in experiments. We get, as you can see on the far right, the right CL max curve, and since the separations are in the right place on the wing, we also get the right pitch break. So these new techniques, both hybrid RANs approaches and wall-modeled large eddy simulation approaches look promising. As Rob showed, you can actually go even more computational intensity, add more grid points, and you can do a wall-resolved large eddy simulation, which is sort of even more physics-based approach. But the computational grids just get prohibitive for these full-scale vehicle-type configurations. So this wall-modeled approach is actually using those large eddy simulation to capture the big eddies, but doing some modeling to ensure that we don't need quite as many grid points as would otherwise be required. Okay, so Rob showed this roadmap. I covered over a lot of it with pictures of progress. Here I just want to really say we are making progress. Things are happening here. You can see NASA is listed as contributing a number of models and tests and wind tunnel entries. You can see we had one test already with this 10% semi-span model. You can see the picture on the left shows that. But more recently and more exciting, we have used that first test to sort of finalize the design. And that finalized design, now we have a model on the right. Here you see it being built up in our 14 by 22 wind tunnel facility. But in fact, this is a model designed for the NTF, a cryogenic facility, where by changing the working fluid from air to liquid nitrogen, we can actually get down to very low temperatures where the viscosity is such that we can achieve flight Reynolds numbers on this. So we can get our validation data at the needed Reynolds numbers that our CFD is trying to predict. So that's really exciting. This test in the 14 by 22 is mainly just to check out the hardware because next spring we'll be sending it over to DLR, to the tunnel in Braunschweig, to do some more work there. Then it will come back and be run in our NTF, a couple different entries, one in FY23 and one in FY24. So that's really exciting. At the same time, we're building a smaller model that we can do a full span test. That will also happen next year. And as Rob pointed out, Boeing is building models, Onera, Kawasaki, JAXA, all building models, all sharing data, all building our understanding of this configuration, all reducing the uncertainty around the data we are getting for this. So this is really neat. I want to add that this is not just about the CFD too, it's about the innovative measurements techniques here to get these measurements. If we're going to do wall-modeled large eddy simulation, we need to understand what those large eddies are. Those are not just surface measurements. Those are off-body measurements. We need to be able to do that. In facilities like the NTF, a cryo facility, that's a hard thing to measure, right? Some of the techniques historically have been developed just for wind tunnels and air. So we have some development to do to be able to get those new measurements and validate some of these new computational approaches. I will say this is also a much bigger effort than the Tcube project. We have collaborations from the mission projects in ARMD. AATT has done acoustics testing, and the ground test facilities, AETC, has been a huge collaborator in this. Of course, they're very interested in understanding how to extrapolate wind tunnel results for flight, while we're trying to use CFD to predict results in the tunnel and then predict results in flight. So by having all of these things together, we're really going to accelerate the progress towards getting the right answer there and understanding what are the effects of the wind tunnel, what are the limitations of the CFD, and getting high confidence in our results. So again, just a brief summary. Look ahead to next year. High Reynolds number test campaign is going to begin. We'll have 2 tests there, so that's real exciting. Rob also talked about the importance of multidisciplinary stuff and aeroelasticity. We're planning a new series of validation experiments in our TDT tunnel at NASA Langley. We are emphasizing uncertainty quantification, and we'll be introducing new stuff on that. And finally, I just added there's a lot of emphasis too on what we can do with artificial intelligence and machine learning to accelerate some of this modeling progress.
All right, good morning, everyone. It's a pleasure to be here today. So I wanted to share some of my thoughts on, next steps towards certification by analysis, but providing more of an outlook, a thought on, the role that the digital thread will play in this. So obviously, like any capability, certification by analysis is really the top of the iceberg, right? There is a number of enablers in the field of people, processes, methods, and technologies that support the realization of certification by analysis. So I wanted to spend a little time going through those with more emphasis on the technology. So obviously, in order to conduct certification by analysis, you're going to need engineers, analysts, managers that need to be very well versed in the tools and the techniques to be used to again, support CBA. That entails that they have the right skills. There's a workforce development perspective to it. There's also a culture aspect to it. We need people to embrace digital. When you talk to the processes and the methods, the first one obviously is the shift from a document-centric approach to a model-based centric approach. And that is very much often realized through model-based systems engineering on MBSC. The second part is when we talk about certification in general, we need to establish confidence. And in order to establish confidence, you need evidence. And as Uwe mentioned previously, this evidence could be obtained through physical tests or simulation, though the two are not mutually exclusive, right? You can actually achieve evidence through physical tests and simulation. When we talk about physical tests, though, there's always a physical trust infrastructure that is in place, right? There's a chain of custody. The person who's running the test has been trained. The tools have been calibrated. There's a number of audits taking place. You have a number of standards you need to abide by. And then there's some statistical analysis that is being done on the results that you achieve. In the modeling and simulation space, however, you don't have this kind of trust infrastructure. And so trustworthiness in those cases is usually achieved through verification, so qualifications of the tools that you're using, and that involves verification, validation, and obviously uncertainty quantification, as we mentioned. And then there's the technology aspect that I'd like to focus a lot more. So kind of talking a little bit about, this equivalent digital trust infrastructure and what do we mean. So there are a number of capabilities that this infrastructure needs to enable. The first one is the transparency and the traceability of the entire model building process. That means you need to be able to understand the specific simulation detail, and that, for example, involves the geometric configurations. You need to be able to understand and keep track of the analysis tools that were employed, the tools input parameters that were used, the coupling framework that was leveraged, the analysis data that was generated, and the validation data that was used. And obviously, this needs to be within a data management system. So it is, again, trustable and accessible. Another part of it is really the documentation of the context of use of models, right? So, and that is usually achieved through metadata. So data about the data and data about the models. And that involves, documenting what was the intended purpose of the model, who developed it, what was the underlying set of assumptions that were made when that model was developed, and then what was the domain of validation, what is the domain of application, do they intersect or not, and really the question is here, do I have the right model for the questions that I'm trying to address? And then the last part is the part that deals with accessibility, explainability, and reproducibility of the simulation or analysis results. Meaning that in addition to having the models documented and accessible, you also need to have the data that was generated by these models linked. You also have to have the verification, the validation data used, the certification data that is available and linked to the models that were used. And that will facilitate things like, as was mentioned before, the fusion of physical data with simulation data, for example, for the purpose of certification. And so all of this lead to this concept of digital thread, which is really the collection of digital artifacts whose consistency is actively managed throughout the life cycle. And what this does is really ensure data and model integrity. Again, ensure that there is consistency in the models and the tools and the data that is being produced. And then you have information about provenance. And obviously, and another key enablers is retention and curation of those digital artifacts. So I kind of wanted to spend one last slide really quick on how this digital thread is relevant to our certification and certification by analysis efforts, and more specifically. So the digital thread really kind of provides this repository to organize, manage, mine, search, and discover the data that has been generated all from research all the way to full production. One aspect of the digital thread is this bidirectionality of information, meaning that all the information that is being generated is linked as an authoritative source of truth throughout the life cycle of the product, from design, production, operation, and so forth. So what this provides now is it allows you to trace all the evidence and the rationale for what decisions were made and why they were made the way they were made. It's going to give you information about where the data is coming from, who generated those models, what kind of maturation they went through throughout the life cycle. Because you have now all this information that is being integrated, it really helps you maintain the complex relationship between things like material, part geometry, the individual processes, as well as the subsequent physical and virtual testing. So you have this full chain of custody, if you wish. Again, because everything is integrated, you're able to understand and quantify impact of specific inputs and variables on specific behavior, but also on performance. You're also able to establish correlation and relationships across many parameters, and that is something that is not easy to do with experimental data alone. And then from there, you can predict performance, validate those results against physical test results, and you can more easily quantify and reduce those uncertainties. Another aspect of the digital thread, as I mentioned, is consistency. And actually, before this was called a digital thread, it was called a consistency thread. So the goal here is, to ensure that all authoritative derivative or successor information is fully compatible with its authoritative parents or predecessor information. So the tool can talk to each other. There is consistency between the geometry and then the simulation analysis tools that are being used. And then the last key is really this the ability to use the digital thread to increase communication, collaboration across teams and stakeholders and customers. because of the qualities of integration and consistency of the digital thread. Again, it's very easy to go back to what was the rationale for specific decisions. So it helps with limit the likelihood of poor communication across stakeholders. It also helps with if you have a latecomers in the decision-making process, for them to understand, what was the rationale again for what decisions were made, and have access to that information as they move along. So, in summary, what I wanted to emphasize is, as we make progress on the tools and the methods for certification by analysis, we need to keep in mind that this digital trust infrastructure needs to be developed hand in hand. With this, thank you.
Thanks. Good morning, or maybe it's more appropriate to say good day now. Well, being now the fourth in a row, I'm running a little bit into the danger of repeating everything, since everything has been said, but perhaps not by everybody, so let's see how I fare with this. Well, and what I'd like to do in the next 5 or 10 minutes is to put this certification by analysis maybe into somewhat greater perspective as it was discussed up to now. And if we are looking at aviation challenges we are facing now, it's essentially the decoupling of growth and climate impact. And on the sketch to the right, you see, well, what happens if we don't do anything with respect to the emissions and so on, the climate impact of aviation, and perhaps what we need to achieve until 2050 to come up with a carbon neutral aviation system. And well, what kind of technologies are running with respect towards this challenge? And there are several. On the one hand, it's batteries, then we have fuel cells, we have hydrogen, and then we have the sustainable aviation fuels. And perhaps, at least my personal perspective, that's why I marked it that way, is that with respect to batteries, due to the problems with the energy density, they will be used mainly for small aircraft. When you go towards fuel cells, due to the power density, these may be applicable for regional aircraft. And hydrogen, when you use it for combustion engines, this may be applicable for short and medium range aircraft. Well, you have the challenge of the tanks and then of the necessary infrastructure which needs to be established. And for long-range aircraft, at least from my personal perspective, it will be sustainable aviation fuels, where we have to face the challenge of availability. We have to produce it in the right amount. Something else, which, at least from my personal perspective, is often overlooked, is, well, with respect to the airframe itself, what we may have to do in order to enable these technologies in the first place is we have to reduce drastically the amount of energy consumed by the aircraft itself. And on the one hand, with respect to enabling these technologies, which all have the problem of energy density and power density, but also with respect to the coming up fuel prices. If you produce hydrogen, or even SAF, this will be a lot more expensive as fuel is now. So this may be a possibility to mitigate the extremely high fuel prices. And now you may ask yourself why I'm talking about this stuff. What does it have to do with certification? Well, if we want to achieve a carbon neutral aviation until 2050, we are talking about high risks, we are talking about high cost, and we only have a short time. And digitalization will be a key technology in order to achieve that. And the certification process, this, if we want to achieve it in this short time frame, this will require this certification by analysis. So this is at least from a personal perspective, the larger picture of that. And it was mentioned already also in the morning by Rob. Now certification by analysis has to cover the whole flight envelope. Usually CFD is done in this, let's say, comfort zone of the design point. But now we have to cover the whole flight envelope, being at low speed, being at high speed, being at flutter, whatever. We have to be sure that our methods are covering the whole flight envelope. So what does it mean then with respect to the requirements for certification by analysis? And again, it's just my personal view on that. At first, the methods we are using, they have to be applicable and they have to have the corresponding prediction capability. This means we have to be able to predict the flight characteristics at the whole flight envelope, not only at the design pod. But then, and from my personal perspective, even more challenging is reliability. What we have to make sure is that we produce conservative results. Conservative here meaning being on the safe side. If we don't establish this conservatism in our predictions, well, then the margins we will have to use when we apply numerical methods will be that large that the question at the very end will be, what is the progress we are going to make? And then the third point is understandability. Well, we have to convince the authorities that our methods are really applicable and reliable enough. This means that, well, also the authorities, not we as applicants, but the authorities also have to understand how is the whole process done? What are the delicate intricacies of this process? And then, as mentioned by Olivia, it's also about repeatability or reproducibility and also predictability. Since all this is more or less confidential data and we have to make sure that these data are not altered or so on. So this means we have to deal with documentation, with archiving, manipulation protection. Well, there has been a first step by this already mentioned COI to provide these recommended practices. And the current discussion, and hopefully in the question and answer session we will come to that, what is required at least to achieve the first 2 points. The other point 3 and point 4, this is then more about the information technology. But first, how do we come to this applicability and the prediction capability, and how do we manage this reliability issue? And just as some food for thought for this discussion, what are the challenges from my perspective on this way towards this CBA with respect just to points 1 and 2? On the one hand, also mentioned by several people now, flight characteristics are an interaction of aerodynamics, structures, and flight control. And therefore, wind tunnel data may be insufficient for a complete validation of our methods. On the other hand, now you may say, okay, let's go to flight testing. Well, those who have done flight testing themselves may know that, well, getting accurate flight test data is very, very difficult. Just imagine, how do you measure CLmax in flight tests? It's not as in the wind tunnel, you wait for separation. But essentially, it's a maneuver you are flying. So when we talk about CLmax, do we have to simulate the maneuver in order to come up with the reliable CLmax? Well, another problem is, well, when we use flight test data for validation, at least for commercial aircraft, these are proprietary. So how do we get the science? How do we come with this from the scientific community to get access to these data? Perhaps, as I mentioned, if when wind tunnel data may be insufficient, perhaps a scaled flight test demonstrator is a means to demonstrate this prediction capability I was mentioning, and also, well, showing that we are on the safe side, meaning that we are conservative. And then if we are going towards this route, how much Mach number and Reynolds number and error elasticity similarity do we need from this scale demonstrator? These are questions which are not so easy to be answered. And also something which at least drives my thoughts around is this process, this mathematical process of uncertainty quantification, is it really sufficient for conservative results? Since we have to make sure that we are really on the safe side. So this are my thoughts, and now we are waiting for your questions. Thank you.
Well, I'm certainly not going to be able to avoid repeating myself. I'll keep my remarks short, but I wanted to make sure I cover at least some of the key points for individuals that weren't here this morning. Just to repeat current trends, we've talked about MBE, we've talked about the improvements in the CFD modeling, and the additional capabilities of oncoming computer equipment. And so all of those are really converging to provide an opportunity to use these higher order or more accurate tools. Certainly we've seen demonstrations that show where the limitations of some of the current tools are, but also a lot of indication of where there's room for improvement, and we're seeing improvement. But for us to really gain confidence and make some very significant further improvements, we really need a set of high quality data that we can then compare to, learn how to use those tools, or make further improvements where required. Mike covered this, so I'm not going to go through much more, but there is a stepping stone approach of how we go from this ground-based, wind tunnel-based validation set to the multidisciplinary to the grand challenge, where we have the ability to predict a priori some of the characteristics that could be that we could do in flight test if we had the right vehicle to do so. I won't cover any more of this detail since Mike covered it, but I did want to go through the challenges that I mentioned this morning about continuing to validate scale resolving CFD tools, continuing to work towards characterizing the component and system level uncertainties, integration and validation of multidisciplinary analysis tools and processes, development of the represented validation tests for that multidisciplinary analysis tools and processes, and then finally have a discussion about, well, what is the appropriate flight test data to validate the predictive flight characteristics, and how would we do that as a community? Lastly, maybe we'll get to this point, but how do we continue to build that regulatory acceptance to really use certification by analysis? With that, I think we're ready to start.
Back to the challenges.
Sure.
So we'll just keep the. Am I on?
Just in case you need that.
Okay. So, so let's start the conversation. I want to thank the speakers for their remarks. As I mentioned, there's a lot of overlap to a large extent, talking about and emphasizing the different elements that we think are important for cert by analysis. So we do want to kind of focus on some of the challenges, right? I mean, we've touched on a number of different topics that are being actively worked. So what I'll do is kick it off with one question. I think that I think to get the conversation started, and then we'll open it up to the audience for questions. So I think we talked a lot about the scale resolving CFD methods, how they're coming online, how we're taking advantage of the increased accuracy of the flow physics that's being modeled. We've talked about a little bit about the UQ, but there's a lot of activities going on in developing UQ methodologies, mathematical relationships, how you go through the process of understanding what the UQ is in terms of numerical simulations. But one thing that I think is really important that maybe we haven't spent a whole lot of time is in really multidisciplinary analysis. So the question really to the panel is, given your knowledge of what is going on today in terms of method development, how can we accelerate that activity to where we can deploy those tools for the purposes of, say, cert by analysis? I'm particularly thinking about aeroelastics. Obviously, that's the first area that would be a critical one to capture and do well, but others as well. Flight controls, for example, would be a part of that. So I'm just kind of curious to know, what we can do to accelerate and deploy those tools, and what kinds of activities that can we do within the community to accelerate the use of those tools. Any thoughts? Gord?
Yeah, well, I'm coming from the scientific community, and when I'm looking back at the CFD development, what triggered CFD development, at least from my personal perspective, was having reference data. And maybe some of you are not aware of this anymore, but when we started with this, it was NACA 0012. It was the RAE 2822 airfoil, and this was computed all over the world by almost everybody. Well, then we came up with the Honora M6 case and so on. And then, we entered into these drag prediction workshops, the high-lift prediction workshops and whatever. But this is almost only about aerodynamics. And if, at least from my personal perspective, if we want to trigger now this multidisciplinary effort in the same way as this really steep development of CFD was. If you look at it 30 years ago, it was some kind of esoteric exercise. It was these validation data. And how do we get now the validation data for multidisciplinary simulations? This, from my personal perspective, is the most difficult question. Mm-hmm. But I think this is going to trigger then this development we need for the certification process.
Okay. Yeah, I would say that coming up with the appropriate use cases to go after getting validation data to drive development of tools and methods is also a key topic that really needs some discussion, right?
Yeah, so I guess we'll add to that, we're talking about the high lift prediction workshop, the AIAA workshop, which is looking at this high lift CRM as the common non-proprietary geometry there. But there's also a sequence of aeroelasticity prediction workshops, and NASA's been working to get those through. And one of the challenges we find is there aren't a lot of modern open data sets there to do some of this validation. So we have been focusing on, dusted off some old ones for the earlier workshops, but we are trying to get a aeroelastic common research model into the TDT tunnel, like I mentioned, which would provide, high quality data on an interesting configuration with modern measurement capability. So we're hoping that we can start moving in that same direction with the aeroelastic approach. I think at the same time, more broadly, we're realizing that some of these solutions for more electric or greener are going to involve coupling many disciplines, not just structures and aerodynamics, and that we need a better capability to couple multiple disciplines at various fidelities across many applications. And we've also been working, I've seen some talks here citing OpenMDAO, which is one of the frameworks we have sort of put together to do that effectively and to be able to optimize across hundreds or even thousands of variables to understand things like thermal management constraints on an electric vehicle that wouldn't necessarily be something we're thinking about, for a transport. But all these are going to be important things and need to be worked. And we are trying to start providing data and framework capability to look at some of that stuff. Mm.
So a question for the panel. It's hard to do all the different disciplines at once. Is it sufficient to do a combination of tests? For instance, whether it's aeroelastic plus aerodynamics, TDT might be a very good example of a facility you could do a CRM type model and provide that kind of information. But then I also worry about, as we come to some of these newer configurations, whether it's a rise engine, that now the power is affecting the aerodynamics. So how do we start building confidence in these combination of disciplines that we absolutely must do?
Very good question.
Where appropriate.
No, I think first of all, it's really, as Jeff said, find the right use cases and then think about what needs to be done. Activate the whole ecosystem. And even if we are speaking about proprietary data, think about, can we do something in order to share that with all the public, in the public domain, with all the university research institutes, and maybe that leads up already to 80% of the way, and the rest then has a manufacturer to do by its own. And but it depends very much on the definition of the use cases, what needs to be done and what needs to be combined.
And to that end, maybe I think we need maybe start thinking about taxonomies, or at least decompositions of, you start with your performance metrics, what it is that you're really after. What are the physics that is involved? And then you start going backwards, like what are the uncertainties that are involved? Which one are you trying to reduce? That will lead to the type of test you want to do, what type of instrumentation you need to have in place and facilities you have in place. So maybe start again from, what is the performance you're after?
And even what facilities are available to do the test
Exactly.
we're asking it to do.
Exactly.
And well, perhaps also coming back to your question about this multidisciplinary, what is necessary, and are we able to do let's say, first 2 disciplines and 2 other disciplines or something like that? I'm not so sure whether this may be a necessary prerequisite, but it will not be sufficient. And if you're looking at the challenges which lie in front of us, then it's also increasing efficiency, meaning we are going to higher aspect ratios. Essentially, we are going to more flexible wings. And whether it's then aileron reversal, whether it's then active flight control, whatever. But these, if we want to go towards this way, these wings need the interaction of aerodynamics, structure, and flight control. And we cannot separate these if we really want to go towards these challenges. And I doubt that with respect to these very flexible wings and the large size of transport aircraft, somebody is going to just go through the flight test and see what happens.
I would even add onto the flight controls the pilot in the loop. This is why I called in my slides it always modeling and simulation, because it can be also a part of the simulation test. But there needs to be some steps before that we have a valid model available to replace some of the flight tests we are doing, maybe also by simulator tests.
All right, do we have any questions from the audience? Okay. Well, let's shift gears
I
a
think
little
there's one,
bit.
Jeff,
Oh.
over here. To your left.
Hello. Carl Sequeira, Flarebright, UK. So I think it was Mike who mentioned in passing at the very end about machine learning and artificial intelligence. That has a whole host of other questions about trust. So my question to you as a group, what perspective, what opinion do you have on machine learning and artificial intelligence in assisting certification by analysis? If you have any opinions at all, of course.
Yeah, no, obviously you're right. If you put active decision making using those processing into your loop and you don't know all the pathways you can go, that becomes a real challenge. And we're looking at things like that at NASA for our more autonomous vehicles like eVTOL, electric vertical takeoff and landing. I think the use I'm talking about here is more as we develop a turbulence model, for instance, can we use machine learning to settle on a better model, to choose better coefficients, to maybe make connections that we're not seeing sort of with our physical intuition, but that the numbers show us are there? Then we could take that model candidate and validate it in a more conventional approach. And it wouldn't be controlling the process, it would be part of the research to getting a better model. So I think that's a little easier task than relying on the machine learning on the fly for flying your vehicle, for instance.
And expanding on that out just a little bit, I think being able to look at the information that, all the data that we collect and looking for where there's some interactions that are going on would point to, hey, you need to look at this. But we need to be looking at, okay, why is this happening, or why is there an interaction we didn't expect, and work to understand why that's occurring. And it can't just be blindly taking machine learning or artificial intelligence and saying, well, the computer said so.
Perhaps a personal comment on that. Sometimes I have the more and more the impression that artificial intelligence, machine learning is seen as the silver bullet, just throw it on it. Well, essentially what's behind all this is pattern recognition. It tells you what happened, but getting the reasons why it happened, this is essentially not answered by these. You may get more access to these data, perhaps you find more data for this explanation, since the pattern may become clearer, but the root and cause, this is something which is not answered by machine learning, at least from my personal opinion. And that's why, especially when we are talking about certification, I think we have to have the knowledge about root and cause.
Yeah, I very much agree. I think that really the challenge with AI, as you mentioned, is the explainability of AI. Understand why you come to this outcome. There are maybe a number of opportunities where AI could be applied, in particular in the edges of the flight envelope, where the physics is difficult to capture and model. And so maybe approaches like physics-informed machine learning, which is really hybrid approaches that combine physics-based techniques with data-driven techniques, could be one way to kind of start making improvement in that area. Maybe another aspect where AI could come in, or machine learning AI could come in, is model calibration, and especially when you have high-dimensional models. There might be applications where reinforcement learning, for example, could be used to help calibrate parameters for specific models, maybe more so than particle filtering is doing. And another aspect is we talked about the creation of aerodynamic databases, right? And to be used for certification purposes. And that will involve that you fuse data for multiple fidelities across multiple timescales, while trying to keep track of the uncertainties throughout. And again, I think this is where specific methods, versional encoder encoders, for example, or deep geometric machine learning could help. But again, I think it's still very much exploratory, and I think there needs to be additional standards developed, and I think ASME is working on some of those for V&V of any type of data-driven approaches.
But especially the data fusion, I think, is one of the aspects we have to work on.
Well, there's opportunities there, right? So we have a lot of test data already on airplanes that look very similar to typically what you want to try to certify, so you want to take advantage of that. It might be a way of using machine learning to identify the areas that are higher uncertainty levels, right? Where to focus the tools and the development of the tools to model those specific areas, right? So, very good question. Any others?
Hi, my name is Robert Hellqvist. I'm from Saab Aeronautics. Here. I have a question on the topic of validation of multidisciplinary analysis, and I guess a lot of engineering disciplines are quite competent in modeling within their own domains, and I was wondering if you could comment on how standards for model exchange could be used to, if they can contribute to achieving a credible, more credible simulations and reducing uncertainty within this topic.
If I may start, I'm convinced that if we really push the data continuity during the process and also to have a single source of truth and we use all the same models, it's helping a lot, or will help a lot in order to make us sure and to validate and not to start every time with another modeling phase. So for me, the answer is yes. I think it will help.
Yeah, I think the whole idea of model-based, system engineering is that we're building that common structure so we can talk across disciplines. Yeah. And it's challenging to maintain CFD codes, but if now we need to port our, aerodynamic flow into a structures code, you have to ensure that all the data structures can read each other, understand that commonality needs to be there. And as you update this code, that commonality needs to be updated here. So we see these codes growing bigger and frameworks growing bigger, and all at the same time, they have to be dynamic because the computer architecture is changing. As we go to GPUs and other things like that, the data structures may need to change to run effectively there. That has to cascade through everything. So we need to coordinate these systems and have that commonality to make sure we don't take a step back every time something in the system changes.
There are some questions, though, I think, in terms of loosely coupled versus tightly coupled on some of the analysis. And maybe that's an efficiency question in terms of how quickly you come to an answer, but I think there's also going to be cases where you may have completely different answers or different legs of an answer, depending upon how you approach the solution.
Well, I think it's again, we are back to this validation data. Where are the critical interactions where you perhaps need a closely coupled approach and where a loosely coupled approach suffices? But, well, I think it's now 20 years ago or so when we started with respect to aeroelastic coupling, just two disciplines. There was also the question whether going with a monolithic code or going towards the loosely coupled approach. From my personal point of view, fortunately, we went with a loosely coupled approach. When you just look at the complexity of the codes for one discipline, this is already daunting.
Yes.
If you have this all into one big machinery, the question is whether this can still be handled by, say, normal people. So from that point of view, or normal engineers, from that point of view, I think this question, as it was raised, how do we manage the interfaces between the disciplines, will become one of the prerequisites which we need if we want to go towards this really multidisciplinary simulation, which is not only aerodynamics, structure, and flight control, but we're talking about electrical systems.
Yep.
How do we figure this into it? Just the engine itself, the engine behavior, and then Uwe mentioned already the man-machine interface. So I think, at least from a personal perspective, how we interface the different disciplines will become a decisive problem.
Which is part of what MBE is all about, right? So it's almost like it's something you have to do this problem, properly, which is what we're trying to do anyway. So yeah, the interfaces are critically important, not only to ensure that you have consistency across the geometry and other things that are important, but also having the ability of the tools to evolve, like you said, right? And that's to me that's the bigger challenge.
Yep.
Is how do they evolve, because they become, and then there's interactions between the tools that have to be taken into account as well. So I think the interfaces have to be all set up, but I don't think that's actually happened yet. We've had on an academic level, we've had a lot of success, coupling different disciplines. Maybe up to 3, maybe, but it's been very academic. And the question is, how do you bring that into a more industrial
Production environment.
Right? Okay.
Simon Knoll, Kinetic. So that triangle at the start, the experimentalists and the flight test might see their world shrinking. But my question is, how do you engage those communities to actually get more from our experiments and our flight test to support the simulation going forwards?
Yeah, I don't think we see it shrinking. We see it focusing into the critical things that capability can provide that we need. One of the things we've seen is we bring computation and experimentals closer together. We're measuring things in wind tunnels we never measured before, like the complete inflow boundary condition, because we're trying to match that in CFD. We're understanding the impact of upstream struts and stuff like that we never looked into before and may have been impacting the results. So bringing these two together and really trying to make an apples-to-apples comparison of a CFD computation, maybe including the wind tunnel walls, with what we're actually running there, has brought great insight into that capability as well. So I think the solution is a coupled one, and I don't ever see a world where CFD is going to be able to do everything. These problems are just too hard, and we're always pushing the boundaries to new physics. We're going to need reality checks. Those will come in the tunnel. The challenge is going to be that the physics we want to know, and that was mentioned earlier, there may not be a facility that can give us that. And are we able to make the investments in new facilities that can provide this critical data? That's going to be a challenge because those are expensive facilities. So You know, do we just project into a simpler problem that we can do? Is that ultimately, you know, going to be effective enough? Or how do we advocate for a facility that can do better with propulsion aerodynamics integration, if that's what's needed, whatever that future is?
And flight controls.
Yeah.
Kind of underscoring Mike's point, as we get into this, let's say we have a process that we are all confident in following. We are still going to need the validation to as Mike said, the reality check to make sure we're doing it properly. It's easy to just push a button and say, well, the computer said so. How do you know you followed the process appropriate? Certainly relies on the individuals that are doing the process. But I think you want to have that additional check to say, okay, does it make sense? Does it compare reasonably to the wind tunnel results? Understanding limitations of the wind tunnel as an example. That all needs to be part of that discussion. So I don't see it necessarily eliminating testing. We may actually find that if we're really focused on the predictive flight characteristics, we may have to do additional wind tunnel testing, which might be a surprising answer. But if we're really trying to represent multiple load conditions or multiple power conditions in the engine, there could be a lot more testing that would be necessary in order to validate that you're doing it correctly.
Rob, you're focusing a lot on the wind tunnel. I would like to bring another aspect. It can be also explains flight demonstrators, scaled or whatever.
Or even previous airplanes.
Even previous airplanes, at least for our internal stuff, yes, can be used in order to do so. And then you might overcome the one or the other problem with the facility you were just mentioning. Of course, then the other problem is to select the right demonstrator, to select the right platform. But that can help in order to produce data which we can use in order to validate our tools.
Well, that kind of brings up one of the questions I definitely want to touch on, because it's kind of the elephant in the room. You know, we've talked a lot about getting adequate flight test data for verification purposes of these tools and these processes. So the question really is how best to do that, and in what way can we bring that information to the community in such a way that we can accelerate progress in cert by analysis? We've had, as you've seen, we've had a lot of success in engaging the community to making progress, and we want to continue to do that. The question is how best to do that when we've got, you know, proprietary issues with flight test data, for example. Any thoughts on that?
To overcome the issue of the propriety, I think is we need something which we can share in the public domain, and the CRM is one of the examples. We have in Airbus the XRF F1, but these are still models which you can use in wind tunnel, which you can use in simulation. I would go a step further and think about really flight test demonstrators somehow to be used in order to make those data then available. But there is a way to go. It's not something which we can immediately jump on. Maybe we have some data already. Fine, let's use it. But for addressing a particular issue, maybe we need to think about going in that direction.
Yeah, perhaps also, well, I completely underline what Uwe said. I think at the very end we need something which is flying in order to cover all, to be sure that we cover all the multidisciplinary aspects. Since if we are building models, well, we are building models, and
Right.
by building these models we have a certain predefined perception which may not cover everything. So that's why I'm really convinced if we want to make this progress, we need some kind of scale demonstrator. Whatever then the scaling is, that's one thing. But the other thing which maybe is a little bit overlooked when one goes towards this route, do we have the appropriate measurement technologies for that? since, as I briefly mentioned, accurate flight test data is not that easy to achieve. So from that point of view, with respect to the development then of experimental technologies, this may also create a completely new challenge for those people.
Yeah, I'm wondering, you know, obviously within the OEMs, we have vested interest to verify and validate our tools, right? And the question is, how do we bring that out and make it common, right? So that's the real trick to this, I think. Any thoughts on how to do that? I mean, are there forcing functions, for example, that we might identify? So, for example, icing is a key technology that affects aircraft design, you know, and so it's important because the regulations are changing on icing, and that will force all of us to think differently about how we do that, right? And so the question is, can we use something like that to drive the development of a common flight vehicle of some sort, or a subscale vehicle of some sort? Just an idea. Any thoughts?
Well, certainly, I think a subscale vehicle is something that is possible, at least in terms of being able to share the geometry and the data. When you get to, you know, our OEMs willing to provide flight test data, you also have to be willing to provide the geometry and all the data that you are aware of on the configuration. And that's going to be extremely difficult.
Uwe and I, we talked about this in the coffee break a little bit, and perhaps with respect to the scientific community and then the OEMs. I think we need this kind of a common representative of a flying vehicle, which can be shared, whatever kind of vehicle this is, similarly as with a CRM, but in quotes only flying. And this may then cover 80 or 90% of the route.
Right.
But the rest, being at 10, 15% or whatever, I think this is the proprietary issue of the OEMs.
Right.
But bringing the scientific community in, we need something like that. And I think it's in the interest of all the OEMs, since from the scientific community, you will get a lot of speed there.
Yeah, it seems reasonable that you're not going to, for a subscale vehicle, for example, you're not going to be able to, you know, have a equivalence to a flight vehicle. There are going to be differences.
There are.
Right, and there are, and so, but
can
that's
you learn from
that's
that?
okay, right? So, I mean, if you can do the subscale, right, with the tools, you know, with some tweaking, you can probably do the flight vehicle, right?
I think what we have to make sure is that it's representative, but it needs not to be exactly similar, but well, that's why I mentioned Mach number, Reynolds number. How important is Reynolds number, for example? Is 10 million enough? Well, then we don't need a large airliner. No way. And I think we should also use what's coming up now, all this unmanned vehicles. So this is a kind of technology we can use for something like that. We don't go towards a manned aircraft, then you have all these certification issues coming with them. So there may be routes to explore, and we can perhaps come up with a representative vehicle which does not cover any real product, but covers the effects on the real product.
Right.
And as you said, if we come to 70, 80 or 90%, but a big portion of the cake can be then solved together. And that's only the last bit, which is then on our side to look in old existing data or whatever, whether it copes with that still.
Right. Excellent. Any other questions?
Morning, Daniel Rexi from Airbus. You have shown, of course, impressive progress, especially also in the calibration against our tools. And Uwe, I like quite much your triangles there, where we are shifting these boundaries. But as we have most likely new technologies coming up, maybe in the sense of transport airlines, disruptive technologies like open rotor propulsion, high aspect ratio, active controlled wings, whatever. Is there a risk that there is maybe the challenge even to keep these boundaries in your triangle, or even the risk that we are falling below this? So will we be able really to harvest off also for those technological dimensions the progress which you have illustrated here? What are your thoughts on that?
As I said, this shifting of the boundaries is very depending on the use case. And you mentioned it. If there are new technologies, we might even start on another area before we can then try to shift it again. No question about that. And in some areas, as I said, for some use cases, it might be relatively easy to go that route. For others, and that is including your thoughts about new technologies, we might start from another basis, and we might even not reach the same border settings. Yes, it is dependent, clear.
I think the roadmap, kind of shows there's some things that look like they're more doable in the nearer term, some that are going to be very challenging and may not even happen by 2040. And those longer term ones may need a lot of still exploratory probing through additional experimental testing or whatever. So it's going to not be a unique pattern. It's going to depend on the application, and we're going to try and start with ones that notionally look more doable. But ultimately, we need to be able to keep this process going and get to those tougher problems.
And Daniel, perhaps with respect to the triangle of Uwe, when we follow this route of getting more trust into our methods, then we will never eliminate flight testing at all. No, but perhaps then, even if we go to these disruptive technologies, we will then be able to focus a lot better on the flight tests, which is definitely required, and where perhaps we can use then simulation data in order to reduce the amount of flight testing. So identifying the critical areas beforehand, before the flight test, I think this will then be, if we have the trust in our methods, this will be then never eliminating flight testing, but in this triangle shift things a little bit.
So I will say that the history of aerodynamics or aerospace in general has been, we've always come up with new things that have caused us problems when they were initially implemented. I go back a number of years, and the first tool I used was Flow 22, a Tony Jameson full potential method with boundary layer calculation included. But it was a wing out of a wall. And we had to make use of that, and we designed actually quite a few products, including the C-17 with that tool. But we put winglets on it, and now suddenly the tool doesn't really work for that. So there's multiple examples where now we have to worry about laminar flow, how are we going to apply that, and how are we going to characterize for all conditions what that might mean to the flight operations. So there's always this additional technology that gets added, and we have to be able to adapt to that and predict as much as we can with the tools we have, but then improve on what we have learned as a result of that first implementation. So it's never going to go away, but that's part of the challenge of aerospace.
Got one to your left.
Okay.
Yeah, thank you. This is Pradeep Raj from Virginia Tech. And on the third bullet there, I have a question. We have talked about validation of MDA tools. And having worked with one discipline, with the CFD applications, you find you have experimental data and the computational data, and they don't match. So you're searching for what might be wrong either in experiments or in computational simulations. So is there any research going on to figure out when we go to MDA, which is by definition multidisciplinary, how are we going to find out when things don't match that the primary sources should be looked into? What discipline? So is there anything going on to say what level of fidelity each discipline ought to be before we integrate them and how we integrate them? And so I'm just curious if any research going on that would be helpful in that. Thank you.
Yeah, the space of possible mistakes is definitely greatly increased, right? And like you say, is the problem with the aerodynamics? Is it with the level of the sophistication of the structural model? Did you use a simple beam model when you need something more complicated? So yeah, you're going to have a more challenging debugging process, and hopefully as we build up the capability, we have test cases, we get insight, we understand effective processes for trying to drill down to that and get a better understanding, rules of thumb about where each technique is appropriate. But absolutely, when you're coupling multiple disciplines, the space of the challenge increases. And it just has to be part of the learning process, I think, as we develop those tools to try and hopefully know what their limitations are and what kind of challenges can arise there. But it's probably going to be more time consuming than it was for a single discipline.
Yeah. And perhaps coming back to the question we had about half an hour ago with respect to artificial intelligence, where I made some little bit skeptical remarks on that. But here in this process, when we have this interaction of many disciplines and we are not exactly sure whether these results are consistent or plausible, here perhaps artificial intelligence or machine learning can be a very good assistance to that. What is plausible or not? If you look at all the data which is available and try to find these patterns in these data and then compare the results you get from your multidisciplinary simulation to these patterns, and fall they out of the usual pattern or are they in the usual patterns? This may then direct you perhaps towards where do you have to look? Is it the coupling process itself? Is it the interfaces? Or is it a single discipline? This may then perhaps guide you a little bit better towards where is the problem located. But I think there is no easy answer to your question. How do we?
I would add too that to kind of talk about what Mike, you had mentioned before about the common research model for elastics. One thing that we have been trying to do on the aero side is have building block types cases where we isolate certain effects, right? And I think that's going to be much more important when we start coupling disciplines together. Can we come up with representative experiments that isolate certain things and then do it in a building block kind of fashion, right? So that we understand whether it's a structural response or aerodynamic response or a combination of both. So I think that's going to be, that just makes it much more complicated, right, and time consuming. But I think that's likely a fallout of trying to do this in a systematic way.
So I do think that we need to take greater advantage of actual visualizing the data, because a lot of times what you see, whether it's a CFD solution or aeroelastic solution, you'll look at some of the details and they won't look right. And that won't answer all of the questions, but it may be a way of at least having a first look through it to say, what is it about the calculation? Should I believe it? Does it look like it's reasonable or not? I think we've seen a lot of flow visualization as an example that we didn't understand until you really went into the flow visualization from the CFD tool. And so is there greater use of that can be helpful is a question.
And maybe a comment on that before we talk about validation. Maybe there's still some work that needs to be done on the verification. And make sure that some of those frameworks are not just random number generators, that we understand what are the assumptions that have been in those frameworks, what are the degrees of freedom, which ones have been locked. And so to ensure that, when we try to reproduce the analysis, we end up with the same results.
Mm.
Let me make also a comment when we compare experimental data and simulation data. We never should forget that also in the experiment there's a certain scatter and there is an uncertainty in it, and that includes flight test. That is sometimes a little bit, it's obvious, but sometimes it's a little bit forgotten. People believe a lot in flight test, and we can believe in a lot of things, but there is a scatter around that.
Well, we're almost out of time, but I do want to touch on one other topic that I think is really the last bullet here in terms of challenges. Now, how do we build regulatory acceptance of the proposals that we've kind of talking about today? So it's really a kind of almost a question to the audience too, particularly if there's any representatives from regulatory agencies. What more can we do here, right? We talked about verification, validation, uncertainty, quantification. All these things are critically important to prove that we have a trusted process. What other things are important here to really build that acceptance within the regulatory agencies?
Well, I think the community approach that we're taking is a big part of that, right? You get consensus across a lot of different communities or pieces of the community that this is a valid thing. That's compelling, right? I mean, it's not just one company saying, we can do this when no one else can. It's saying, no, the community out there has been working together and agrees that this tool is applicable for such a certain circumstance. That seems to me would accelerate belief by the regulators. So I think this approach that we're taking is a great way to do that.
And maybe having more participation as we do these experiments to show what are we doing and how are we doing it, so that they have an understanding and appreciation of that testing and how we validated the tools.
And this is exactly what we did in our recommended practice document, AAAA, where we involved the FAA and the EASA into the establishment of the document.
Excellent. All right, well, I want to thank everybody. I want to thank our panelists and speakers for a wonderful discussion. And I want to thank all of you for attending and participating. Again, this has been recorded and will be available, I think, tomorrow at some point. So, yes, thanks, everybody.